think it's live. Yep. I think we are live. Hello, viewers. Welcome to another episode of Let's Talk Science. This episode is supported by Science for Society, Indian Humanists, and Babu Gognani Humanists and Rationalists Arena. Today we have a very special guest in our episode. And before introducing him, let me also welcome Master Teja Begari, our young amateur astronomer, and also Amol Mane, who is joining us again from Sydney. Welcome, Teja, and welcome, Amol.
Thank you, sir. It's a great pleasure.
Yeah. So now our special guest, Dr. Patrick Das Gupta. He is Professor of Astrophysics, Department of Physics and Department of Astrophysics at Delhi University. Welcome to our show, Dr. Patrick Das Gupta. Okay, so it's a really pleasure to have you on our show today. And Teja would like to start asking few questions and share his experiences with you, sir. Go ahead, Teja.
Yes, sir. So basically, we want to start this discussion by remembering one of the eminent astronomer, Dr. Ratnasri Nandiwada, who served as director for the Nehru Planetarium, Delhi, and who was responsible for the improvements of historical astronomical instruments here in India. Dr. Ratnasri Nandiwada is someone who always had spare time for young individuals who are interested to know about the universe. We mourn the demise of Dr. Ratnasri Nandiwada, who left a very rich legacy we must nevertheless celebrate. On a lighter note, Dr. Ratnasri Nandiwada is the spouse of our special guest today, Professor Patrick Das Gupta. We agree with you, sir, and Dr. Ratnasri Nandiwada will always be remembered. Over to Prasad, sir.
Yeah, thank you, Teja. So, thank you for remembering her before this show, and I would really like to looking forward to hear from Dr. Patrick about his association with her. And before that, I would also like to start with how Dr. Patrick Das Gupta, you got interested into astronomy and science and mathematics in general, and what are your motivating factors?
Yeah, so when I was a kid, then I sort of encountered certain textbooks on magic tricks. These belong to my uncle, and I started reading them. And to impress my friends, I would participate in showing them magic tricks. Later on, as I advanced to class 7th and 8th, I realized that most of the magic tricks were based on physics, chemistry, optical illusions, etc. That is what motivated me to slowly drift towards the subject of physics. And with that, I got interested also in mathematics. So in the early age, my strong interest in physics and mathematics actually resulted from magic tricks.
Yeah, that's good to hear. I think, in fact, most of the people, not just in actual strong scientific field or scientists, like even normal people who are into science popularization, science communicators, and you take any of them, like even Amol, who is here with us today. So most of the people actually got inspiration from some introduction of book reading in their primary to late primary to mid high school kind of thing. But I don't know how now with the new generation, with the not so time for, or a lack of attention for long periods of time to go read books, like how it is happening. But definitely that's a good thing to hear, sir. And Amol, can you also join the discussion? And what do you think uh, you want to ask Dr. Patrick?
Sure, sir.
By the way,
So,
Amol is an astrophotographer joining from Sydney, and I think the image that in the background is what he has taken from somewhere in Sydney.
yes, so the image that you see in the background, this is obviously the center of the Milky Way. This was taken from a place called the Wormholes, which is
Yep.
Australia's first dark sky preserve, about 500 kilometers north west from Sydney. So it's very interesting, sir, to hear you talk about the similarity between magic and science. Yeah, unless you actually get into the details and explore science, everything it really feels like it's a magical place. There. So that's very interesting to hear how you got into science. My question probably I had a question. This I only wanted to ask an astrophysicist, which was. In the last century, we sort of we as the human species, we discovered these two important theories of physics, the quantum mechanics and the theory of relativity, and they seem to explain a lot, almost everything that we see in the universe, right from the large black holes to the everyday objects that we see in, and it explains gravity. On the other hand, we have the microscopic world, which is explained very nicely in quantum mechanics. Now, what I understand, again, coming from more from a layman's perspective, is that the two don't seem to sort of don't seem to talk to each other. Or the maths doesn't make some teams seem compatible, and there seems to be a great effort by scientists, Einstein, Stephen Hawking, and even today, for scientists to somehow reconcile these two theories and to arrive at what Stephen Hawking used to call the grand unified theory. People have called it something like the quantum theory of gravity and so on. So my question to you is, do you think such a effort is realistic? And if it does culminate into this unified theory of everything, what would it look like? Can you share some insights there?
Yes. As we all know, that there is no conflict between quantum mechanics and special theory of relativity. The problem appears when one wants to formulate the general theory of relativity, which say relativistic theory of gravitation, in quantum mechanics formalism. The main problem with the unification of quantum mechanics with general relativity is that in general relativity, gravity is not a force. Rather, gravity is manifestation of the non-Euclidean geometry of the space-time. So, in Einstein's view, gravitation is not a force, rather, it is the curved nature of the space-time geometry that appears to us as gravitational force. And because of this problem, where other forces like electromagnetic forces, the strong forces that bind protons to neutron in the nucleus, the weak forces that cause radioactivity like beta decay, etc., all those forces were put in conjunction with quantum mechanics without any problem. And that's the reason why people like Salam, Weinberg, Glashow got the Nobel Prize for the electroweak unification, or even before that, the quantum electrodynamics, which put electromagnetic forces in the quantum domain, fetched the Nobel Prize for Feynman, Tomonaga, and Schwinger. And then the strong interactions mediated by gluons among quarks. They also, that QCD, the quantum chromodynamics, which is a quantum theory of strong forces, that also fetched Nobel Prize for people like Gell-Mann and others. So the general relativity, which is the next hurdle, how to bring general relativity in the quantum domain, the first success, so-called success, came with the string theory. So string theory, which physicists like Schwartz, Green, they developed way back in 1974, and they gained acceptance by late 70s and early 80s. In the view of string theory, fundamental particles are not point particles, but they are tiny strings. How tiny? The size is of the order of 10 to the power minus 33 centimeter. And in string theory point of view, all fundamental entities are made out of this tiny oscillating strings. And what they discovered was a closed string, that is a string which is like a loop. So a closed string or a loop that corresponded to graviton. And that was what caused excitement among the particle physicists in late 70s and early 80s. And the whole mathematical theory of string theory developed. And in the point of view of string theory, gravity is also a force mediated by the quantum excitations called gravitons, which are zero mass excitation of closed loop strings. Now, the string theory is quite advanced. It can reproduce at the lower energy level the standard model of particle physics with, of course, certain bottlenecks. But the problem with string theory is that it has not been verified in experiments, because the predictions of string theory, if you want to test them, you have to have accelerators which have energy of the order of 10 to the power 19 giga electron volt. Now, our large hadronic collider, LHC, that can accelerate particles only up to 1 trillion electron volts, or maybe up to the level of 10 trillion electron volts, but nowhere close to 10 to the power 19 giga electron volts. So therefore, string theory, although it's a consistent mathematical model that in principle unifies gravity with other forces at a quantum level, is an untested theory. Similarly, in 1960s, Abhay Ashtekar, he got a great breakthrough in pure quantum mechanical aspect of general relativity. He and his collaborators succeeded in taking general relativity, where gravity is the manifestation of geometry, and he arrived at a quantum theory of geometry. And this is another independent quantum gravity approach called loop space quantum gravity, or in short, LQG, loop quantum gravity. That has been also mathematically successful in various aspects in solving subtle riddles, just like string theory, namely the quantum nature of black holes, removing the black hole singularity using quantum gravity. Again, unfortunately, the LQG, or loop quantum gravity approach of Abhay Ashtekar and his collaborators, have not been tested in the experimental laboratory, precisely because of the same reason. To test, one needs accelerators which produce particles of energy at least of 10 to the power 19 giga electron volts. So, although, to answer your question, that there are mathematical models which have put quantum theory as well as general relativity together, the only problem is we don't know whether these theories are what nature follows. That is, whether these are the correct theories, because after all, in science, we accept a theory only if the theory and its predictions are experimentally verified. I hope I have addressed your question.
Yes, sir. Yeah, you have. If I may just sort of as a follow up to that, what you just explained. Now, let's assume that we do build up that theory. What would be the area that are currently mystery to us that would get solved using these something like this unified theory?
Very good question. So, some of the things which both the string theorists as well as loop quantum gravity people have been addressing is that in classical general relativity, our universe began from a singular point around 13.8 billion years ago, namely the Big Bang singularity. So both string theorists as well as Abhay Ashtikar-led loop quantum gravity people have shown that with their versions of quantum gravity, you can remove this Big Bang singularity. Similarly, there are uh, both these two distinct approaches have shown that black hole singularity, because the classical general relativity shows that when gravitational collapse of a sufficiently massive object occurs, it leads to formation of black holes where entire matter collapses to a single point, and therefore the density becomes infinite. The geometrical curvature, the so-called Riemann curvature components become infinite, and infinity heralds breakdown of physics. So these are the singularities, and both the approaches have shown that black hole singularities can be avoided by these two approaches of quantum gravity. The next puzzle, which both of them are trying to solve, is something called information loss paradox related to black holes. Around 1974, when Hawking showed that when you apply semi-classical quantum fields studies near the event horizon of a classical black hole, then from the semi-classical quantization of fields near the event horizon of a classical black hole, it turns out that the event horizon acts as a black body, radiating thermal particles. But this creates a conflict with quantum theory, because you can form a black hole by using pure quantum mechanical states. But if after formation of black hole, the event horizon starts radiating thermal particles are not described by pure quantum mechanical states. And this creates a problem in quantum mechanics, because quantum mechanics shows all physical processes will evolve a pure quantum mechanical state to pure quantum mechanical states, not to thermal quantum mechanical states. So this problem is called the information loss paradox in black hole physics, because after all, when a black hole completely evaporates away, you have this paradox that you form the black hole using pure quantum mechanical states, and now after that black hole has completely disappeared by evaporating into thermal, radiating thermal quantum mechanical particles, a pure state has become a mixed state, which is completely disallowed by quantum theory. And this information loss paradox is people are trying to solve it both from string theory point of view as well as from LQG point of view. And many physicists like Samir Mathur, who currently is a professor at Ohio State University, using string theory, his fuzzball approach is one of the leading candidates to explain the black hole information loss puzzle from the string theory point of view. But there are other sort of scenarios also talked about the so-called firewall approach, wherein the event horizon is surrounded by a very hot wall that destroys all particles. Similarly, uh, Subrat Raju of ICTS Bangalore, he has another contentious way of solving the information loss paradox from string theory point of view, which uses holographic uh, conformal gravity theory, which is part of string theory. So the jury is still out. We still don't know whether information loss paradox has been solved through string theories. So these are some of the problems which can be, in principle, be solved in the future by string theory or by the loop quantum gravity approaches.
Okay. All right. Yes. Thank you, sir.
Most welcome.
I have a question here,
Sure.
Dr.
Please go ahead,
Patrick.
Mr. Yeah.
So, as you mentioned, like, in general, science is the best tool that we have to understand the universe and its functioning around us. And I'm sure uh, now they are calling STEM or STEAM, where they are grouping the related fields of sciences and the mathematics and other things, engineering and technology, as a way of uh, uh, you know um, preparing curriculum for future scientists or citizens. So in which mathematics also has a lot of importance, but we normally see mathematics as just a set of vague equations and complex rules, and that are required to by heart and memorize and perform. And normally most of the mathematics we study as part of our academics, we don't tend to use it in the normal day-to-day activities. But how does the scientists and especially astronomy and astrophysicists, which parts of the mathematics do they use on a daily basis? And also after that, the extended question is math really the language of the universe? Or all the mysterious numbers that we come across, like the speed of light and the electromagnetic forces that holds atoms and molecules, and all these theories of how the universe works relies on these mathematics. So did we get to understand why it is so, or can we actually uh, uh, make sense of the universe in the mathematical terms?
Very good question, Mr. Prasad, because these two questions are very dear to me. I have actually written two articles on these two subjects. First of all, your first question. So, mathematics, it started uh, with civilization itself. People realized that counting is very important. So people, when civilization was growing, they realized that you have to count your cattle stock, you have to weigh your grains, like whatever is being produced in the farms, rice or wheat, etc. So quantitative ways of dealing with nature began with civilization itself. So counting, measuring weights, then architecture, geometrical ways of uh, viewing the world, the space, three dimensions, building straight lines, straight edges, and Pythagoras theorem, which was well known to Mesopotamian civilization, Greek civilization, also Rigvedic texts in Sulva Sutras talk about Pythagoras theorems. So counting, which is the uh, cornerstone of arithmetic, and space time visualization, which is what led to geometry, these were the were essentially the underpinning of the development into abstract mathematics, that as the civilization progressed, mathematics started evolving in a very rapid way. And people immediately realized that mathematics is based on two concepts. One is logic. Logic is a set of rules by which you always end up from an assumption to a conclusion without having any inconsistency. So, whether it's the Greek or philosophers like Aristotle or Euclid who used logical systems to systematize, axiomatize geometry, or whether the Nyaya system of our Vedic structure, Nyaya is the Sanskrit school of thoughts where logical tools were explored. So, logic is one of the first things which first pillars of mathematics. The second pillar is quantitative measures. So mathematics gives great amount of emphasis on characterizing properties using numbers. So mathematicians won't say, oh, how beautiful is the flower, because beautiful flower has no numbers in it. While mathematicians will say that if you take a triangle, the side, if you have a right angle triangle, the side measures A units and the other perpendicular side measures B unit, then the side measuring along the hypotenuse, if it is C unit, then you can prove that square of C is A square plus B square. So all aspects of mathematics are quantitative and based on absolutely rigorous rules of logic. So, and that's the reason why in the beginning, most children dislike mathematics. They get scared of mathematics because of these two pillars, namely rigorous logic, and second is the quantitative and cold way in which mathematics develops. And the branches of mathematics which are very, very useful in all walks of physics, whether experimental physics or theoretical physics, astrophysics. The branches are algebra, geometry, calculus, differential equations, integrals and differentiations, coordinate geometry, statistics. Statistics is one of the mathematical branches which not only scientists but even social scientists use in a very, very elaborate way, whether it is the economists or whether it is the sociologists or whether it is the commerce people. So statistics is one of the most useful subjects that are used by both scientists, mathematicians, as well as the social scientists. So, to summarize, algebra, calculus, differential equations, coordinate geometry, geometry, uh, statistics, these are some of the mathematical areas which are universal. We all use it in our day-to-day life. But if one wants to do string theory, quantum field theory, and general relativity, then tensor calculus, group theory, differential geometry, Lie groups, abstract Lie groups, Lie algebra, and very, very abstract mathematics become essential if one wants to go over to subjects like string theory. In fact, string theory is closer to abstract mathematics than any other branch of physics. In fact, that is the reason why one of the leading string theorists, I'm sure all of you are familiar with his name, Edward Witten. He actually got the Fields Medal in mathematics. because his work in string theory, it opened up new areas in pure abstract mathematics. So that's my comments regarding your first question. So mathematics, certain parts of mathematics are essential for both theoretical and experimental scientists, but certain aspects of mathematics which are regularly used by theoretical physicists are uh, differential equations, group theory, uh, tensor calculus, abstract Lie groups and algebra, and so on. Now let's come to your second question, Mr. Prasad, and that is that you pointed out that the language of the nature, the fundamental language of nature, seems to be mathematics. The question is why? And this question was have been wondered about ever since physics was born. Like Galileo, who is considered to be the father of physics, Galileo was 400 years ago. He talked about the great application of geometry and algebra for setting up postulates and laws in physics. Of course, even before Galileo, Archimedes, his buoyancy theory, the so-called buoyancy theory he chanced upon after that Eureka episode when he jumped out of the bath, realizing the greatest importance of buoyancy. He also applied mathematical tools to understand certain physical phenomena. And after that, Kepler, the great Kepler, for the first time, he understood planetary motions in terms of ellipses, major axis, minor axis. He applied the geometry and coordinate geometry to explain the planetary motions. And then later on, Galileo, when he started physics, and later on, Newton, who not only used physics, he independently of Leibniz, they invented calculus to explain many evolutions of physical models. And there, after that, physicists never turned back. They realized that mathematics is very, very useful, culminating in a great essay written by the Nobel laureate Eugene Wigner. He wrote an essay. It's a delightful essay. I'm sure all of you would be interested in reading it. The title of the essay, if I recall correctly, is On the Reasonable Efficacy of Mathematics in Natural Science or in Physics, something like that. It's a great essay in which Wigner wondered that why is it that mathematicians who try out their own imagination, abstract imagination, in coming up with newer ideas in mathematics, time to time, their ideas become so useful in physics. For example, let me give you an example. When non-Euclidean geometer like Riemann or Lobachevsky or Gauss, they were trying to develop abstract branch of geometry going beyond Euclid's geometry into non-Euclidean geometry, they never bothered about the real world. They said that, well, what if I don't accept the fifth axiom of Euclid's geometry? I relax the fifth axiom. Can I develop new kinds of geometry? And they gave independently. Lobachevsky gave his own version of non-Euclidean geometry. Riemann gave his own version of non-Euclidean geometry. And these were all before 19th century, before 20th century. And when Einstein was trying to create a theory of gravity which is consistent with his special relativity, he realized that only way to do that is to view gravity as manifestations of non-Euclidean space-time geometry. He realized that, but he did not know the non-Euclidean geometry concept. And when he talked to his friend who was a mathematician, his name, I'm slipping, is a very Marcel Grossman. And now I got his name. Marcel Grossman, who was a mathematician. When Einstein talked to Grossman, Marcel Grossman said that I think what you're referring to, mathematicians have already talked about it. It's called tensor calculus used in non-Euclidean geometry. And then Einstein himself went ahead and learned about tensor calculus, non-Euclidean geometry, and he applied these to create the general theory of relativity. So, in other words, Wigner was wondering why people like David Hilbert, he had developed his own abstract space. Today we call it Hilbert space. And lo and behold, in 1920s, when quantum mechanics was taking shape, people realized that quantum mechanical states are part of an abstract Hilbert space. So these are the things, surprises, that mathematicians do their work for elegance, beauty in their abstract ideas, and time to time, some of their abstract synthesis turn out to be the language of nature. And it's a surprise, certainly. And people have pondered about it. And I have written an article. If you just, in the Google search, say mathematical year, 2014 mathematical year, I have expressed my ideas as to why it should be. My ideas are as follows: that language of nature better be having no inconsistency. Because how do we know what are the language of nature? We measure various quantities and try to find out what are the relations between different measured physical quantities. And all measurements are, the output of all measurements are all in terms of numbers. Whether it is length measurement, time measurement, weight measurement, they're all part of numbers. And the original mathematical system, like arithmetic, geometry, they were all developed by looking at these measurements. So the original mathematical language was based on actual real world measurement. And because the original mathematicians, who were not to be distinguished from physicists, if you go back, all the older mathematicians were also physicists, like Gauss, Newton,
Tycho Brahe,
Pascal,
Edmund Halley.
So they were both physicists and mathematicians, because the original mathematics was being built based on what you measured in the real world. So in the beginning, physics and mathematics source was nature itself. But then, of course, mathematicians, they have their own idea of beauty and patterns in their thoughts. So today, if you ask what is abstract mathematics, it is a logical subject which deals with patterns in human thoughts based on logical analysis. So they went into abstract mode, and they created many, many different abstract modes. There are many abstract mathematics which still do not have applications in the real world. So abstract number theory, people have wondered that are there number theory results which are applicable to physics? It turned out that one of the abstract results of number theory, namely Ramanujan formula, has been recently shown to be applicable to string theory. But otherwise, most abstract ideas of number theory, whose champion was, of course, the great Ramanujan, have not been applied to physics. For example, one doesn't know why prime numbers, which play such a great role in number theory, what is the relevance of prime numbers in physics? So far, no one has found out, are prime numbers saying something unique in physical model or in nature? No one has an answer to it. So there are great many abstract mathematical ideas which have no application in physics or in understanding nature. But certain subsets of mathematical development become useful in physics. According to me, the reason is that nature cannot be inconsistent. And the only quantitative and non-inconsistent theory we have is mathematics. Quantitative, why? Because nature is learned. We learn about nature by a dialogue maintained by doing experiments. We keep on do measurements by changing this uh, environment in nature, cause and effect study. So in science, cause and effect is very important. Mathematics doesn't have cause and effect idea. But mathematics has logical way, starting with an axiom or a set of axioms, you logically follow and end up with a theorem. And the theorem, because you have logically proceeded from a group of axioms, obviously, in the context of mathematics, the theorem is absolutely correct. By correct means is logically correct, logically true. So there is no inconsistency. And nature must be also be consistent. And because nature is all about quantitative measurement, whatever language we use to describe nature, it must be one based on numbers and geometrical ideas, that is length, time, space, and numbers, and it should be logically consistent. And therefore, the only language we have which has logical consistency and are based on numbers and geometrical ideas is mathematics. All abstract mathematics are built on these basic facets of logic, numbers, geometry, and coordinate geometry. All abstract mathematics are more abstract forms of these basic ideas, which to begin with started from the study of nature itself. And this is what my impression as to why uh, the language of nature has to be based on mathematics. There is another idea which I have talked about in my second article on pedagogy of mathematics, is that we human beings have limited sensory uh, facilities. We have only 5 senses. And through certain measurements, we can go beyond our 5 senses. For example, in astronomy, we use radio astronomical techniques or infrared astronomy, which cannot be perceived by our 5 senses. Our eyes can't see radio waves, our eyes can't see infrared waves, and so on. But through technology and scientific advance, we have gone beyond our 5 senses. But nevertheless, to understand the radio waves, we have to convert the radio waves through transducers into things which can be perceived through our 5 senses, either electrical impulses in the cathode ray oscilloscope, which we can see, or by touching whether something is becoming hot or something is cold. So eventually, even the tools which are not directly accessible to our 5 senses, we perceive them by finally converting them using transducers to signals which can be
understood by us.
perceived using our 5 senses. But what if the real nature has fundamentally some properties which cannot be even perceived through extended technology. After all, nature is much, much, much more complex than human brain. Our human brain is a product of billions of years of natural evolution. So nature is much, much, much more complicated or abstract than the human beings, and also what we today perceive as our world is only one aspect of the real nature. Just like Plato's allegory of caves, where Plato talked about people who only were confined to caves and they only saw the shadows on the cave walls and interpreted the outside world by looking at the shadows without ever seeing the real world. And similarly, the story of the six blind men touching the elephant and trying to figure out what a real elephant is like. So because we are limited to our five senses, we cannot perceive the real abstract nature. And this was also talked about in the Vedic philosophy, Upanishadic philosophy of Adi Shankara, namely, although I don't per se now believe in Adi Shankaracharya's idea of Advaita, which says that that the self-consciousness and the ultimate reality, namely the Brahma, they are identical. Brahma and conscious self is identical, and the rest of the world is an illusion or Maya. It was an interesting philosophical development around 800 AD when Shankaracharya proposed it, but I don't adhere to that philosophy. But that itself explored that the real nature of Brahma is not what we see as the so-called world. According to Shankaracharya, the real world is Maya. The actual nature or the actual true world is beyond that, which he termed it as Brahma. And he, in his Advaita philosophy, unified Brahma with self-consciousness, while the Dvaita philosophers, they made the consciousness and the Brahma distinct. So philosophers have talked about the fact that nature may not be accessible to human beings, and those branches of philosophy is called metaphysics because it is beyond the physical world, metaphysics. But the problem with metaphysics is that you can create many, many theories, metaphysics theories, but by very definition, metaphysics cannot be tested through any experiments. So how do we know whether my metaphysics theory is correct or whether the metaphysics theory of my friend is correct? So that is the dichotomy we end up with when we talk about metaphysics. And that's the reason I always say that only testable philosophy is the scientific philosophy. Scientific philosophy and scientific epistemology is the only part of philosophy which we are sure of because we can test them in the laboratory. But what is the link with mathematics? Because the real nature of the fundamental world is beyond our senses. According to me, the only way we can get a glimpse of this fundamental real world, fundamental real nature, is through abstract mathematics. Abstract mathematics is like our sixth sense, because abstract mathematics talks about the logical relation between concepts which are beyond our measured world. So a part of the abstract mathematics may be the one which can actually give us a glimpse of the real abstract nature which are beyond our physical senses. And therefore, to summarize, the reason why mathematics is important as a language to understand nature, first, it is the only quantitative branch of logical knowledge. And second, because of its very abstract way of developing mathematical concepts, it can give us a peek into the real abstract nature through the use of abstract mathematics, since abstract mathematics is our sixth sense, because it's based on our brain. Brain is the abstract part of our thinking, is our like sixth sense.
Thank you very much, sir. So actually,
so these are, of course, my thoughts. They have to be taken with a pinch of salt.
Yeah, absolutely.
These are speculations of mine.
Yeah. In fact, it's very nice to even try to understand why math is the language of the universe, because at some point most of the people, they get scared of it, and they have the doubts on the usefulness of that, even the abstract mathematics. But as you said, the logical, the ability to deduce something and prove something or disprove something, and also the consistency of the nature, how it behaves or interacts with other things, is what makes the mathematics the language of the nature or universe, if I can say that. And it also I feel that, yeah, even if we find some intelligent, extraterrestrial intelligent species anywhere outside our solar system, for example, they also have to do the math. Maybe their number system may be in a different way, like they may not be using a decimal, as we have 10 fingers, we are used to decimal system, but their number system may be different. But again, they also have to do the math to actually become technologically advanced.
That's very important, that the future ahead is that our children, the new generation, must love mathematics. So in my second article, which I have called something like reasonable efficacy of pedagogy of mathematics, there I have suggested some ways how to attract children to the world of mathematics, is that our museums, normally if you go to any museum, you will find sections dealing with very surprising aspects of science, like water falling out of a faucet, which is not connected to any pipe or something like that. So people get fascinated. Magic tricks, people get fascinated. And then museum, they will tell you that these are based on certain scientific ideas. So my suggestion is that all museums must have interesting tricks based on mathematics. After all, many card tricks or coin tricks or games are actually based on mathematical puzzles. So to draw children into the world of mathematics is because all children, they get fascinated by surprising tricks, surprising card tricks. So certain card tricks which are based on, no matter how you shuffle, you'll find that the cards are ordered. They always come in order. These are all based on permutation and combination branch of mathematics. So you can draw the children to mathematics if you have very interesting tricks that are based on mathematics in the museums, all museums. And the second thing is, if you look into the park, normal children's park. I'm right now in Hyderabad, and when I look out of my balcony, I see children so excitedly playing in the parks, sliding down, swinging. If in all parks, if you have certain small unit where counting using this gigantic abacus or shapes, showing triangles or squares or interesting properties of triangles and shapes, using some activity, even though not all children will participate, some children will gather around, just like children, they cooperate when they play either cricket or football. They cooperate with each other, they discuss, they argue, they fight. Similarly, some children will gather around these small mathematical tricks, come counting, come geometry. In a small region, in parks, they will discuss, they will present their awe, they will argue. These are the ways of getting out of the phobia, mathematics phobia. And our educationists, if there are any educationists viewing this program, they must pay attention that only way to make India go ahead is that our children must be interested in mathematics, because the digital world is progressing in a very, very rapid way. Artificial intelligence, quantum computers, artificial intelligence based on quantum computers are the future technology. And these are all based on abstract mathematics. So if our next generations have to participate in an active way, they have to concentrate in learning mathematics by being passionate about mathematics. Because only if one loves and is passionate about a subject, one learns in a very effective manner. So these are my suggestions, which I have written in that second article on mathematics, which is, I think, titled as On Reasonable Efficacy of Pedagogy in Mathematics, which is a version of the Wigner's original title of On Unreasonable Efficacy of Mathematics. So, yeah.
Thank you very much, sir, on that addressing
Mr.
that
Prasad.
question. Yeah, definitely we will have a look at it. I myself personally, and I resonate with what you said about in the importance of mathematics, even for physicists and astronomers and anyone who is into science. Actually, at some point they have to do math as well. I mean, nowadays. It's a lot more advanced than it was 400-500 years back, and it's relatively, I can say, I think, easy for someone to actually do good science if they have a real good base in mathematics, unlike Newton's or Tycho Brahe or Edmund Halley, some 400-500 years time. So they had to actually go out and invent, say for example, like calculus, to take their physical sciences, their experiments forward. But yeah, it's I think we are relatively in a better situation now, but there is still a lot more to learn and understand about the universe. But the only way to that is science, and it has it needs a lot of fundamentals in mathematics as well. So with that, I'll give the questioning chance to Teja Begari. So Teja, go ahead and bring your interesting questions. So you have for Dr. Patrick.
Sure, sir. It's actually a great pleasure to be here. So I have a few questions on light and about the expanding universe. So my first question is, can a person, can an individual surpass the speed of light? And if hypothetically that is done, what would happen to that particular individual?
Sorry, I didn't get your question. Is the question that what if one moves faster than the speed of light? Is that what the question?
Is it possible to surpass the speed speed of light. And
Okay.
and if
Okay.
that
The
is done,
first thing is that special relativity forbids us, forbids anything to move faster than the speed of light, because from special relativity you can prove that any particle whose rest mass is m, if it moves its speed v, then its measured mass will be m divided by square root of 1 minus v square by c square. And therefore, from this relation, you can immediately see that if v becomes c, then the measured mass will become infinity. If v becomes greater than c, then square root of 1 minus v square by c square will be square root of a negative quantity, which will give you imaginary number. And mass, which is same as energy, cannot be imaginary. So therefore, special relativity tells us that nothing can move faster than the speed of light. And special theory of relativity has been verified again and again and again in many, many experiments, including the particle accelerators like the LHC, or even before that, particle accelerators like Bivatron, Tivatron, and so on. So therefore, special relativity forbids any object to move faster than the speed of light. Your second question was, what if something moves faster than the speed of light? Now here I must mention that George Sudarshan was an Indian origin theoretical physicist. He was very clever in realizing that you can circumvent around and talk about particles that move faster than the speed of light. He called them tachyons. And how did he beat the special relativistic condition? He did it by saying that what if certain particles have mass which are pure imaginary? That means their mass is square root of -1 into some number. Then such particles can move faster than speed of light, because 1 square root of 1 minus v square by c square, if v is greater than c, will produce one imaginary number that we cancel with the numerator of the imaginary number of the mass, rest mass, and then you will get a real quantity. So tachyons, he theoretically postulated that you could have faster than the speed of light particles called tachyons, and he developed a full-fledged theory. But the problem with tachyons is that tachyons, if they exist, they interact with other particles, then what would happen is that the other particles will become unstable. And that is the reason no one likes tachyons to be present in the real world and interact with other particles. Because if tachyons interact with other particles, you can prove mathematically that other particles would become unstable. Why? Because they will give more energy to the tachyons, and when tachyons energy increases, they slow down, unlike normal particles. This can be mathematically proved. So while if you take away energy from tachyons, then tachyons start moving faster and faster. So they have counterintuitive properties, these tachyons. You might say, what if tachyons don't interact with rest of the particles? Then yes, tachyons can exist. Tachyons as faster than c moving particles can exist. But because they don't interact with normal particles with which we are made out of, we can never detect tachyons. Because to find a particle, detect a particle, we must be able to interact with the particle. Otherwise, we can never know about it. The fact that I am able to see your picture is because light from your face is falling on the computer screen, that is generating some signal. It is going through space, finally coming into my computer. So there has to be interaction between other particles. And tachyons, if they don't interact with the other particles, then we will never be able to measure them. And that is where mathematics role comes in. So tachyons, as a pure mathematical field, can exist. But this is pure mathematics come out of an abstract thinking of Sudarshan and his collaborators. They might be very well existing, but we can't perceive them because they don't interact with the other particles, confirming that mathematics can play the role of sixth sense. So tachyons can exist in the real world, but because they don't interact with the real world particles, we can never find their existence. I hope I have answered the question.
Yes, sir. And next question is about the momentum of light.
Sorry, what is the
It is
question?
about momentum of light. So we know that every particle which has mass has momentum, but light has no mass. How does it have momentum?
Very good question. Here, I should point out that the rest mass of light is zero. But as you know, relativity says anything that has energy E has mass E divided by C square. The celebrated E equal to mc square formula, which says anything that has mass m has energy mc square. Anything that has energy E has mass E divided by c square. So light's rest mass is zero, but any existing light has energy, and therefore its inertial mass is non-zero. Its inertial mass is E divided by c square. And you can prove that anything that has energy and moving with speed c has a momentum E divided by c. It can be proved even in classical physics from electrodynamics. Electromagnetic fields, they move with speed c, they carry energy, and one could show that they carry momentum also. And this was known even before special relativity. And because electromagnetic energy carries momentum, so therefore there is radiation reaction. So when an electromagnetic wave falls on a mirror, gets reflected, the mirror recoils because some amount of momentum from electromagnetic wave gets transferred to the momentum. And so is it true for photons. Photon of energy E has a mass E divided by c square, and also photon of energy E has a momentum E divided by c, and therefore it has momentum, and therefore it can exert pressure.
Yes, sir. And the other question is, this is from the audience actually, asking why is the universe expanding and into what is the universe expanding?
Very good question. Universe is all about our three-dimensional space and one-dimensional time. So the universe is 3 plus one-dimensional space-time. The expansion of the universe is not analogous to a ball that is expanding. A ball that is expanding is a finite volume ball. It is expanding in space. Our universe is the entire, it occupies the entire space. So the universe expansion is the entire space is expanding. To understand it more carefully, one has to go through general relativity. In general relativity, gravity is the geometry of the space-time, and the expansion of the universe is actually the geometric expansion of the space. So when I say universe expanding, what I mean is take any two galaxies that we see, and the galaxies are not bound to each other. It's not the galaxies of a galactic cluster, but any two cluster or any two galaxies far apart from each other. And if I measure the distance between them, then as time progresses, the distance between two galaxies far apart, or the distance between two clusters of galaxies, that distance is increasing with time. That is what we mean by saying the universe is expanding. So therefore, it is not expanding into anything. The entire space is expanding. As to the question, why universe is expanding and not contracting, the simplest answer is that the initial condition. When the universe was born, the initial condition was due to an impetus. The universe was created with an expansion. To give you a physical analogy, if I'm holding a ball, then I can either release the ball, then the ball will be falling towards Earth, and the distance between the ball and the Earth will be decreasing. It's like a contracting universe. While I can choose a different initial condition. Instead of dropping the ball, I can take the ball and throw it upwards. Then for a while, the distance between the ball and the Earth will be increasing. So it's like the expanding universe. So the general relativistic model that describes our universe has two solutions: expanding universe as well as contracting universe. But because we see from Hubble, as Hubble showed, that distant galaxies, light from the distant galaxies get redshifted, which essentially means that the space between galaxies and our galaxy is increasing and causing the cosmological redshift. And that tells us that the initial condition with which Earth, with which the universe was created, is an expanding universe. And that's the reason why universe expands. But some people have also used another idea, because we also know the present observation from type 1A supernovae suggests that there is some exotic matter called dark energy, which has repulsive gravity. Some people have suggested that if whatever caused the universe to be created, if there was also sufficient amount of repulsive gravity source, namely dark energy, then when the universe was created, there was a gravitational repulsion which caused an expanding universe to begin with. But these are all speculative theoretical models. We don't know whether they are correct, because the beginning of universe, it falls in the realm of quantum gravity. And as we have discussed in our first question answer session, we still don't know what is the correct quantum gravity theory.
Yes, sir. So one last question from my side, and then we'll go to the rapid fire questions. So what exactly are wormholes?
A good question. So wormhole, again, is a theoretical idea. Uh, uh, Perhaps it originated from Einstein and Rosen's thing about black hole, where they connected the black hole, and because general relativity is also time reversal symmetric, so they said that if matter can collapse to form black hole, the time reversal of it, that is, if you run the movie backwards, you will find matter coming out. Instead of collapsing, matter will be expanding out from each other. And Einstein and Rosen, they created a theoretical model in which matter collapsed and it was linked to another part of the universe with the so-called Einstein-Rosen bridge, where in the other part of the universe, the collapsing matter appeared as expanding matter. So the throat, that means instead of saying that black holes form by matter collapsing to a single space-time singular point, instead of a point, there is a narrow throat, then the matter can collapse, pass through that narrow throat, and re-emerge in another region of the universe as white hole. And this narrow throat is called the wormhole, because it is like a wormhole through an apple. If you have an apple if you take one point and the diametrical opposite point of the apple, you want to go from the point to the diametrical opposite point, you have to move all along the surface of the apple, and you will take a long distance along the circumference to go to the other point, right? But what if there is a hole which a worm has created from this point to the other point? Then you can go diametrically opposite. It's a shorter distance passing through the wormhole. And that's the reason why physicists and the mathematicians coined the word wormhole, where if instead of a singularity, if you have a narrow throat connecting to the other region, this narrow throat is called wormhole. And what can be shown is to create a wormhole, you need an exotic type matter which has sufficiently high repulsive gravity. And then later on, people like Kip Thorne and other collaborators showed that even if you create a wormhole, it will be very unstable, immediately collapse to form black hole. So it is not possible, according to their calculations, it is not possible to have a stable, large wormhole which will connect one black hole space-time to another white hole space-time, because a large wormhole, even if you create, it will be very short-lived. It will collapse, it will be unstable, it will form a black hole. But again, these are highly speculative mathematical ideas. We don't know whether they are correct, because if you show that, well, there are other ideas which can be used from string theory or loop quantum gravity, and if you can create stable wormholes, that will be quite exciting, because people like Kip Thorne show that if you have a wormhole, you can actually build a time machine. You can go back and forth in time. So yes, that is again using mathematics as sixth sense. You can, think about things that are not immediately tangible in the real world.
Yeah, so this clearly shows that math is the language of the universe.
Yeah, in fact,
Yeah.
I think all previous questions, repeat the same thing. Like, your is it possible to go beyond the speed of light? And this one wormhole thing, where if someone can quickly pass from one point to other without having to travel the whole distance, and again, if he can, he should be able to see the past in his presence, which is kind of like a time travel. But again, we understand that from the math, just like when the Uranus was is it Neptune, right? Neptune was discovered by accident using mathematics. So they found the irregularities in the orbit of Uranus, and they decided that there should be something here, which should cause this one. So
Yeah.
so
Parallel
even
precision
without
number.
having to see the existence of a new planet was itself was guessed from using the mathematics. So that says how consistent the language of math itself is across the universe. So
Correct.
thank you, sir. And yeah, I think Amol has some rapid fire questions. Quickly, he can
Yeah, please go ahead, Mr. Amol.
Okay, thank you, sir. So these are just some sort of questions that we generally have at the end of the session, just to get a feel of how you feel about certain topics in a very sort of quick rapid fire round. So okay, so there'll be three options for the first couple of these questions. So what do you think is the greatest threat to humanity in the next 100 years? So option A would be an asteroid impact. Okay, option B would be climate change, on a global climatic change, and option 3 would be artificial intelligence and the takeover by machines.
Very good question. And if it is direct threat to humanity, I would actually go for option B, namely nuclear war. because you have said 100 years.
Right.
Yes, climate change is a big thing, an asteroid thing is a big thing, but 100 years is a short time scale for climate change or asteroid to create catastrophic disaster. But in the near future, I mean, seeing the current situation about nuclear uh, countries which have nuclear weapons going into wars, that will be, in my view, in the coming 100 years, the greatest threat. Because imagine, because of some reckless uh, action, if someone presses a nuclear warhead to be launched, it would immediately cause a chain reaction of people launching nuclear warheads towards each other, and that would create a catastrophic disaster. So, according to me, it is the nuclear war, the threat of an impending nuclear war, which is the greatest threat to humanity. But yes, climate change, asteroid striking Earth, they are also very big threats. But climate change, if we can slowly adopt green techniques, we can delay the climate change. Similarly, by using sensitive and highly resolved telescope to study incoming asteroids, we can use space-based technology like firing rockets at the asteroid to deflect the trajectory of an asteroid. One can safeguard Earth to some extent from climate change and asteroid collision to some extent. Yes, artificial intelligence, if unsupervised and unmonitored mushrooming of systems endowed with artificial intelligence is allowed, then in the future, artificial intelligence that is based on quantum computers, we don't even know what kind of impact it will have, because just like no one could predict how internet will revolutionize the earth, so quantum computer endowed artificial intelligence, it can take the AI systems to another level altogether, and we are still in a primitive state to predict what is going to happen. So if the AI systems develop their own quantum level free will, not the normal free will that we human beings have, where I can suddenly exert my free will saying that, oh, I have a free will, I'll just leave this session and go out. I can do that. Of course, I'm a sensible person, I will not do that. But we human beings have free wills. A quantum computer based artificial intelligence can have a free will of a different level, and it can create a havoc for human society. So I think about it because I am also very fond of science fiction. I write science fiction stories myself.
Okay.
So, so I have time to time, I have tweeted that these are the dangers of artificial intelligence. So whoever is involved with research on artificial intelligence, in particular with quantum computers enabled artificial intelligence, they have to be very, very careful about the do's and don'ts of what AI should be allowed to and what AI should not be allowed. By the way, these were already thought about by the science fiction author Isaac
Isaac
Asimov.
Asimov, the 3 laws
Yeah, the
of
three laws of
robotics.
robotics.
And even with those
Uh,
laws, like, it was not a happy ending there.
yes,
Because,
yes,
they strictly follow the laws. I think as we saw in the movie I Robot, right? Like,
yes.
it's
But
the
there are other stories of robots by Asimov where he shows how the laws can create bizarre situation.
yeah.
So he was a pioneer in, for the first time, thinking about that we must not build robots which can harm human beings. And similarly, today we have to go several levels ahead, because artificial intelligence, which are based on quantum computers. Of course, today, quantum computers have not become yet a reality. There are many hurdles to cross over, because quantum mechanics requires coherence, and how to have uh, the units that cause quantum computation remain coherent is a big bottleneck, and people are researching. But once you have quantum computers where parallel quantum computing can go, the present computers, it is stepwise. It doesn't do parallel computing. With quantum computers, a whole new ball game will be created. And I'm sure many people, many futurists are giving ideas as to how the world dominated by quantum computers would be. So just like internet created completely a new world and a new world order, quantum computers with internet and with AI will create completely a revolutionized world.
Right.
We can't even predict what exactly is going to happen.
Right.
And therefore, the researchers must pay heed to how to make safe AI systems.
Yes, all the futurists from the technology space, we call it the technological singularity, the term obviously borrowed from black holes. So because you cannot foresee what's going to happen beyond that event
Exactly,
horizon
exactly.
in time.
Because the free will, if we give complete independence to free will, the free will can create disaster. Just like if I give complete free will to myself, I can start doing all kinds of crazy things, right?
Looks like
So,
yeah.
so free will has to be also controlled.
Looks like it applies both for the artificial intelligence and the human intelligence as well. So as we are intelligent, but are we intelligent enough to avoid the self-destructing in the mid to long run is one of the questions again that bothers humankind. So yeah, go ahead, Amol.
All right. So, okay, I'll ask one. So, I'll probably not have options because I think you can think of more options than me, Professor. So, I'll just ask the question. So, what do you think is the most important discovery in physics, especially in the 21st century?
Very good question. Again, this will be a somewhat biased view, because, of course, I don't know the whole of physics. Right? So I have a limited knowledge of physics. And if I were to name ten outstanding discoveries in the physical science in the 21st century, I will say graphene, the two-dimensional carbon monolayer. I'll put the discovery of graphene as one of them, because graphene and graphene related material science is already revolutionizing the field of nanomaterials and nanotechnology. My second item would be the discovery of supermassive black holes. Certain quasars have been shown to have supermassive black hole with mass greater than 10 billion solar mass. And it has created a puzzle because these quasars, the fact that we are seeing the quasar, the light,
early stage
when the light started from this quasar, the universe was only about 1 billion year old. Today, the universe is 13.8 billion years old, 8 billion years old. While the light from these quasars started when the universe was only about 1 billion year old. So one of the challenging questions is, how do you get more than 10 billion solar mass supermassive black holes when the universe was so young? It's a challenging question. And I myself research on it. So therefore, the reason, so obviously my bias as to why I put discovery of 10 billion solar mass black holes as my second. The third is the serendipitous discovery of fast radio bursts. Lorimer, one of the Australian astronomers, where you are, Mr. Amol. So Lorimer, while looking at the archival pulsar data, he discovered that there was a single peak radio burst, and he termed it as fast radio burst. But later on, many detectors in the couple of years, they have actually seen in real time, they have detected fast radio bursts. And we still don't know what is the real nature of fast radio bursts. So these are mysterious objects, and possibly the field of fast radio bursts are going to revolutionize astronomy. Possibly, of course, it could be that they are giant pulses from exotic pulsars. If that happens, then it's not revolutionizing astronomy, but it might happen that fast radio bursts are due to some exotic astrophysical beasts, which no one has imagined even now. Then astronomy will be surely revolutionized. Just like when quasars were discovered in 1963, or pulsars were first discovered by Jocelyn Bell in
Little Green Men.
1977. So it opened up completely new astrophysical ideas. So if fast radio bursts indeed are due to some completely exotic astrophysical beasts, then we are in for a surprise. So FRB, therefore, I would say 21st century's real-time discovery of FRBs is one great achievement. Fourth, I would say that topological insulators and quasi-particles like Majorana fermions and axial Higgs particles in material physics, these are really revolutionary discoveries in condensed matter physics. Their implications might be very high, probably they will lead to the discovery of room temperature superconductors. As you know, one of the holy grails of superconducting research is to have room temperature superconductivity. Way back in 1986-87, when Bednorz et al. They discovered high temperature superconductors, wherein they showed that lanthanum's cuprous oxide, when you dip them in liquid nitrogen, they become superconductors. They led to the whole new field of high temperature superconductors. But they were not room temperature superconductors. Superconductors are material in which current flow with zero resistance. They have also other remarkable properties like Meissner effect and um, uh, things like flux quantization and so on. So room temperature superconductivity will revolutionize our electrical engineering technology, because with zero resistance, you'll be able to transmit current. So all these advances with topological insulators, quasi-particles like Majorana fermions, axial Higgs, etc., they might herald in the holy grail, namely the room temperature superconductivity. As of now, room temperature superconductivity has been achieved at highly dense layers of um, sulfide system, hydrogen sulfide and other things. But they are, of course, not practical because they are ultra dense two-dimensional regions where room temperature superconductivity has been achieved. What one needs is normal high temperature superconductors. Then I would say that discovery of Higgs boson in the Large Hadronic Collider was another great achievement. Although they were predicted way back in 1964, but the discovery of the actual, I mean, after all, in science, we will believe only when we finally discover something. So before LSC discovered Higgs boson, there were a lot of theoretical models which tried to go beyond Salam-Weinberg-Glashow model, which was based on Higgs boson. But all those models have been ruled out after the discovery of Higgs boson. So Higgs boson has been one of the greatest discoveries of 21st century. Then I would say that many molecular biophysics results, like genome understanding of human genome, I would say is one of the most important discoveries of the 21st century, because not only understanding of genome has given rise to the whole idea of genetic medicinal research, which can uh, help us in the real future, but it is being used in archaeology and to sort of solve certain mysteries concerning history. Particularly, for example, genome sequencing has been research is going on to find out the mystery about who were the Indus Valley people, were they different from the Indo-Aryans who composed Vedic verses, etc. So a lot of research is going on the historical puzzles based on genome research. Then among other researchers, I would say that gravitational wave detectors like LIGO and Virgo, which led to the direct detection of gravitational waves, which were predicted by Einstein even more than 100 years ago. But from 2015 onwards, now LIGO and Virgo detectors have been detecting a large number of gravitational wave sources directly, and that has led to discovery of black holes whose mass is as high as 70 times or 90 times bigger than sun's mass, which were not predicted in the stellar evolution theories before. So discovery of such high mass black holes, stellar mass but high mass black holes, have led to a resurgence of stellar evolution theories. So therefore, LIGO and Virgo detectors, I would say, have been 21st century's biggest contributors. Similarly, the use of type 1a supernovae as standard candles by people like Reyes, Perlmutter, and Schmidt, who inferred the fact that not only the universe is expanding, that we knew from Hubble's time, but the rate at which universe is expanding is increasing in an accelerated fashion, leading to the I don't know. I was again logged out. Suddenly there was an interruption.
Yeah,
So
just
let
5 seconds. That's it.
So thanks again to be back. The whole discovery by Perlmutter, Schmidt, and Rice using type 1a supernovae to say that universe is permeated by some exotic matter, which is termed as dark energy, whose pressure is so much more negative that it can cause repulsive gravity, is one of the 21st century's biggest discoveries. And they were, of course, awarded Nobel Prize for it. Now, there is another astronomical measurement which is very, very striking. Of course, the last word has not yet been said, and that is the problem about the value of the Hubble parameter. You know, the study of cosmic microwave background radiation that led to the idea that the Hubble parameter has a value about 68 kilometers per second per megaparsec. But now, recent analysis by Rice et al. Using Hubble space data show that the local part of our universe, when you measure the Hubble parameter value is about 73 kilometer per second per megaparsec. So that has created what astronomers call as the Hubble tension. Hubble tension meaning one value of 68 kilometers per second per megaparsec you get from CMB studies, while the other 73 kilometers per second per megaparsec you get from local astronomical studies. This tension might lead to a complete review of the cosmology we know of. So these are very exciting things, and we don't know where the things are going. Similarly, the neutrino mass, we know that the neutrinos have non-zero rest mass. The older models of Salam, Weinberg, and Glashow, the so-called electroweak theory model, was built on the premise that the rest mass of all varieties, 3 varieties of neutrinos, is 0. But then, with the discovery through atmospheric neutrino oscillation that happened in the 21st century, I mean, the final nail in the coffin was struck in 21st century, and the fact that neutrinos are having non-zero rest mass have given rise to a whole new set of theories like seesaw mechanism to give masses, which predict a very heavy neutrino called sterile neutrinos. Of course, these are at the theoretical level. We still don't know whether the sterile neutrinos exist. But the discovery of oscillations in the atmospheric neutrinos, whose last word was said in 21st century. Of course, there's a whole long history starting from 1970s onwards. And because of the neutrino oscillation, new detectors have come up, the so-called ice cube neutrino telescope, and there is an Indian neutrino telescope, the INO, Indian Neutrino Observatory. Unfortunately, due to environmental controversies, INO has not yet started off. But many of the new astronomical facilities concerning neutrinos, they have been launched in the 21st century, and they might revolutionize the branch of neutrinos. So all I'm saying is that the neutrino observatories have come up in the 21st century, although results regarding breakthroughs have not yet come. But the fact that neutrino observatories have come up in the 21st century has heralded neutrino astronomy. So I would still put them as remarkable achievement in 21st century. And similarly, I would say that many of the vaccine discoveries after the corona pandemic, so the vaccines have really, it stalled this COVID pandemic. And I would say that hats off to all the developers of COVID vaccines. They would be one of the greatest discoveries.
Absolutely, sir.
In the
Yes.
21st century. So I think I'll stop here. And obviously, the list is biased because with whatever limited knowledge I have, and you can go on like the electric cars and the self-driven cars. They are also 21st century discoveries, which are important technological discoveries. But
Yeah. Yes. Thank you, sir. And it's a pleasure sort of hearing you speak with such passion on the both on the breadth and the depth of these subjects. Yes. Thank you.
Awesome.
Right. And so just one last question I have, which is we spoke about the technological sort of singularity in which perhaps the word singularity is hijacked by the technology field, which is from astronomy, but we really don't mind that so much. But there's another sort of area which has hijacked the world with the word, which we're not always that happy, which is astrology. So, and this comes up a lot with us amateur astronomers who speak with the public and science communicators in general. And I think it was Carl Sagan who lamented, saying that there's always a column in the weekly newspapers or the daily newspapers on astrology, but there's nothing on astronomy. So, any suggestions on why is that? Why is this fascination for the general public on astrology? When we understand it's a pseudoscience, and there's not much of evidence backing these claims which are made. And time and again, all these can be attributes to coincidences or just human psychology. But still, astrology is one area which seems to compete against astronomy. Sometimes even seems to have more popularity in the mass public than astronomy.
Yeah, I think the popularity stems from insecurity resulting from the the vagaries of human existence and human fate, uh, and any aspect that provides some kind of hope to human beings uh, against the vagaries of future, people will go for it. I mean, it's a fact that human beings are plagued with disease, uh, lack of wealth, lack of jobs, uh, debt. So these which are not in the control of human beings, they create great deal of misery. And if a group of people say that you can bring down the misery through certain means, either through study of horoscopes in astrology or any kinds of other pseudosciences like tarot reading or palmistry, people will go for it. I mean, if today I announce that I have developed a new way which will give hopes and happiness and ease of mind by my way of technique, people will flock to me. So, although my technique would be purely fraudulent, so because of this, it is very difficult to make human beings, some of the believers of astrology, uh, to tell them that astrology is not science. It doesn't predict, because you can always give examples to them saying that, I still remember when Sachin Tendulkar had captained the cricket team for the World Cup. Many astrologers came, predicted that India is going to win that World Cup series, but India did not win. So when you point this out to astrologers, saying that you have never predicted most of the things correctly, they will immediately say, oh, we did not, because these were the parameters we were using in our prediction. We needed some more parameters to be known. We did not know, and that's why but that's not science. In science, we use the Popper's criteria that of falsifiability. If you have predicted something and if it is falsified, you have to rule out that theory. But astrologers don't follow the Karl Popper's idea of ruling out their theories. And that's the reason why astrology is not a scientific theory, because some scientific theories are falsifiable. A scientific theory must have a prediction. Based on the veracity of the prediction, either you'll accept the model or you throw the model. That's how science progresses. So astrology doesn't fall under the purview of falsifiability, and that's the reason why astrology is a pseudoscience. But as I said, that human beings, they have their other faculty too. Every aspect of human life is not logical. After all, we also go for recreation, which gives us happiness. When we hear music or when you see a great painting, we are filled with happiness. So these are not part of our logical thinking. Affection, emotions, sentiments are part of human mind, and therefore there are different fields of human creativity like music, art, literature, dramas, movie making. They are all very important because they cater to this side of our mental faculty. The problem with astrology is that if they say that we are only acting as counseling, we are counseling people to be hopeful and mentally peaceful, I have no problem with that. The moment they say that it is based on a scientific principle and astrology is a science, that is when I have a problem. So if you just say that, well, astrology is a way of giving hopes to people, calming them down, well, that's then part of psychotherapy. It's okay. But as long as they don't claim it's either a part of astronomy or part of science. So
Yep.
Yes,
I
yes.
think
Thank you, sir, for that answer.
we are close to 1 minute before this stops. So let me, if you are all okay, Amol, let me thank Dr. Patrick Das Gupta for participating in this episode of Let's Talk Science, and we are very happy to listen to your suggestions and experience, sir. And we would definitely like to meet some other day for sure. I think Teja will make sure it will happen because we have a lot more to talk and discuss about, not just physics, mathematics as well. So yeah, let me congratulate. Thank you, Amol, for joining from Sydney, and also Teja Begari for inviting Dr. Patrick Das Gupta. So this episode.
I thank everyone. I thank all of you for this platform. So
the pleasure is all ours and our viewers for sure. So yeah, this is the episode in Let's Talk Science, and I also thank all the technical team behind this and all the members from Indian Humanists and Science for Society. Thank you very much, and we will see in another episode of Let's Talk Science. Thank you, everyone.
Thank you.
So take care. Have a good day. Bye for now.
Thank you, sir.
Bye.
Thank you.